Hello everyone, thanks for joining. I hope that everyone is doing fine. So today we have the pleasure of having Professor Leopoldo A Pando Zayas from University of Michigan and also from ICTP. And he's going to talk about precision holography. Yeah, Leo, you can start.
All right. All right, I hope you can see my screen okay. So thanks a lot for the invitation. It's great to be able to give this talk. I guess I cannot say it in Indian land, but in Indian space, because as you will see, most of what I'm going to talk about was pioneered and highly developed by Ashok Sen. But so what I'm going to be explaining today is about precision microstate counting for AdS black hole entropy, and it's based on these works that you see on my screen with a number of people, but most importantly, Alfredo, who's a graduate student at CISA, and then the other people are Wen Lee, he's a graduate student in Princeton, and the other are senior people that don't need to be push too much. So the main problem that we are interested in is, of course, the entropy, black hole entropy. We are interested because of this formula here, the Bekenstein-Hawking entropy formula. This formula, just writing it down, tells you that it encompasses a lot of really interesting physics, thermodynamics. You see Boltzmann constant. There's, of course, gravitational, Newton's constant, and relativistic, and of course, quantum aspects. You see H bar there. So this formula is like the levels of the hydrogen atom for quantum gravity. And of course, the string theory in '96 provided already a microscopic explanation for the formula. That's really what we're after. But now there have been a new wave. There's a new wave of microscopic explanations in the context of AdS CFT, which I think is quite important, and it might lead us to a better understanding than the solution with the deep brain technology of Strominger and Buffer. So this story, to my knowledge, initiated with this work, very interesting work of Benini, Christophe, and Zaffaroni, who showed that the Larsen limit of the topologically twisted index of ABJM correctly reproduces the leading term in the entropy of magnetically charged black holes in asymptotically AdS4 space. So this is a mouthful. I will unpack all that in the talk, but this is, again, a microscopic derivation of some entropy, and we are interested in understanding a little bit more about that. So these developments that started in 2015 have now been extended to dionic black holes in massive 2A, many different situations where you have magnetically charged black holes, but also more recently to rotating and electrically charged black holes through the superconformal index. So there's been like a really powerful development in the context of AdS CFT of understanding the microscopic entropy of this black hole. And of course, one thing that I would like to focus in this talk is this point that in some cases, not in many cases, but in some cases, we have been able to find agreement beyond the leading end term, so beyond the Bekenstein-Hawking term, and in more precisely, agreement in some logarithmic corrections. And in the context of this analogy with the hydrogen atom, this is like going beyond the Bohr energies. And I like this because, of course, when at some point before you knew quantum mechanics, you could derive the Bohr energy levels just by thinking that the electron is a planet going around the nucleus, etc. So the physics is completely wrong, but the answer is correct. And this is unless you know really something about the electron degrees of freedom and quantum mechanics, you will not really understand what is going on, even though you might have gotten the leading term correctly. And I will, if I have time towards the end of my talk, give some evidence that something along those lines might actually be happening in the counting of entropy as we know it. Okay, so this is sort of like my motivational slide. I think for string theory, people, this is very important, very well motivated problem. But I think that this is quite interesting, even beyond our small community. So it's more important in general for physics. So the outline of what I want to talk today, first I will, as I said, I will unpack some of the phrases that were used, like the topologically twisted index of APJM theory. I will then discuss briefly the magnetically charged black hole and how to compute the logarithmic corrections in quantum gravity. This is, again, not very recent work, but nevertheless, I think it sets the stage for more recent developments that I want to talk about, which are in particular this part here, where I discuss logarithmic corrections to entropy for some black holes in AdS4, magnetically charged and electrically rotating, but they come from M5 brains, so they are slightly different, but in some sense they have an advantage. We can compute much better. And then, if I have time, I want to talk a little bit about some developments. Again, this is all very preliminary about the entropy counting for AdS5 black holes beyond the leading term. So, okay, if I have time, I'll talk about this, and then I will conclude. So let me briefly remind you what the APJM theory is. It is a three-dimensional Chern-Simons matter theory with this gauge group, UN cross UN, level K and minus K. So this was obtained by Aharoni, Bergman, Jeffreys, and Maldacena a while ago. So the matter sector is in by fundamental representation. This is a superconformal free theory with n equals 6 supersymmetry. In the general case for K, but for K equals 1 or 2, this is n equal A supersymmetry. And one way to really pack the information is in this quiver diagram, and you can see the global symmetries that I represented here. This is, of course, n equal 2 notation. So the topologically twisted index of APJM was formulated by Benini and Zaffaroni in general for any n equal 2 field theory, and also discussed by Honda and Closet and collaborators in 2015. And essentially, you can compute it by evaluating a supersymmetric partition function for these cases, for these theories on S1 cross S2 with a topological twist on S2. That's essentially your crash course on what the topologically twisted index is. A Hamiltonian way to think about it is really like a version of a Witten index with some particular chemical potentials, all right? And again, the charges enter through some relationship with the Hamiltonian, but okay, that's a little bit less technical, more technical. So this index can be computed using supersymmetric localization. That's I will briefly explain how that is done. But one thing that you gain on top of that is that, in fact, you can very quickly, if you know the index for S2 cross S1, you can understand the index in any Riemann surface of genus G times the circle. All right. So let me very briefly and mention what this topologically twisted index is. So this is the metric of S2, right? Cross S1 with radius beta, and I have a background R charge, which is given like this. Then the index, the topologically twisted index can be computed using localization. So you have to sum over some magnetic charges that form part of the localization locus. Then there's some contour integral. This function is a meromorphic form in Cartan-valued complex variables that I will either denote as X or as U, but they are related in this fashion. And so I can introduce also flavor magnetic flux, and the localization is, again, this is a separate issue, but it's now a very important tool. And the key aspect is that what you will get is an answer that has a classical part and then one loop corrections, and that's it. This is the exact part. And so just to give you an idea, the classical part in this kind of integration comes only from the Chern-Simons part. All right, and then the one loop you can compute for for the gauge group, and it has this form. Okay, so I don't want to go too much into details because we can very easily get lost in some of those aspects. But the important thing is that that you can write an explicit formula for this topologically twisted index. As you can see, this formula, I don't want to go into too many details, but the key thing is that this formula is evaluated slightly differently. So here you're summing over solution to a Bethe-Ansatz type of equation, which I have written here. All right, again, it's not super important, the form. I just want to clarify how things are done and what the answer is. And essentially, once you solve this equation, you can plug back, and that is the answer for the topologically twisted index. All right, so you can think of this as a 2n by 2n matrix. So the 2n by 2n matrix B, this B calligraphic here, is the Jacobian that relates the variables, these holonomies xi, to these variables bi that I introduced, so sort of like the Bethe variables. But let me take away a lot of all the jargon and the dust in this story. The bottom line is that if you're given some chemical potentials delta A, and then you can rewrite more conveniently using this YA, and these variables, these are the integration variables. What you have to do to compute the topologically twisted index is solve this 2n by 2n algebraic system of equations for the holonomies UI. And once you have these sets, you plug it back into the expression that I presented in the previous slide, and you will get the topologically twisted index, right? It's completely algorithmic. It's something that, in fact, in one of my papers, I had an undergrad student help me tremendously with this. So this is very clear algorithmically. I give you a 2n by 2n system of equations. You solve those equations, you plug it back in this expression right here, and you get the index. And more importantly, the index is exact in n. This is not an approximation. I solve numerically, I know the answer for any n. All right, this is quite important. And that's all. So, but now, of course, what you want to do is to let's try to extract some physics from this process. So, of course, the equations, the numerical equations that I showed to you are for this holonomies UI and U tilde I, the two gauge groups of ABGM. And of course, you can just compute, as I said, and plot them in this plane. This is just one particular plot. But we know this is not the most efficient way to compute this, to attack this kind of problem. The most efficient way is to try to introduce some eigenvalue density. But now, because this is complex, I have to introduce two, and there's a relationship. But with this leading order eigenvalue density, I can compute the topologically twisted index. This is what Christophe Benin and Zaffaroni did in their paper, and they obtained this formula here. This is the answer, essentially. From this, of course, you can get the entropy of the black hole doing a Legendre transformation. But I want to do a little bit more. I emphasize that numerically, this is an exact in n, exact result in n, so I can push that a little bit more. And I can try to go beyond large n, beyond this was the leading piece that Benini, Christophe, and Zaffaroni computed. So now I can try to explore what is going on here. Because again, it's a numerical problem of just trying to fit. I know, of course, from some general principle that the answer must organize itself in this kind of expansion. So I can try to compute this. And that's what we did with my colleague, Jim Liu, and former grad student Vimal Ratti, and Wenli Zhao. So here, for example, I show you how I change the maximum number of n, and I do my fitting. I do it for some different values of fugacities. And the most important thing in this table is of course, this column here. These columns represent the coefficient of the logarithmic term in n. When I have all fugacities symmetric, I have a number here, which is very close to -0.5. And I can go away from that very symmetric point. And I see that basically this number remains the same, more or less. For a theory, this is exactly -0.5. So that is what I extract from my numerical fit. So I can, of course, understand this term, but this is a little harder. But this is sort of essentially what I want to focus, that the numerical analysis of the topologically twisted index, this is a field theory computation, teaches me that there's a correction, a logarithmic correction with that coefficient minus a half, okay? So to summarize, the leading, this part here, the n to the 3/2 terms is the term obtained by Benini, Christoph, and Zaffaroni, and exactly reproduces the Bekenstein-Hawking entropy of a family of extremal AdS4 magnetically charged black holes. They can be embedded in 11-dimensional supergravity. So my goal is now to try to see from the supergravity point of view if I can reproduce this very same contribution, right? But as I alluded, yes.
Yeah, sorry, I had a question. So in this, if you take this exact expression in n, and then is it understood what are all the contributions that can contribute? Like because we don't quite understand fully non-perturbatively the bulk theory, right? The bulk theory is an M theory and so on. Like, do we know like all the, I mean, all kind of ends that will contribute? Is it understood?
Right. So I will move on to the gravity side, to the bulk right now. If you give me a moment, I will tell you what is known. But the short answer to your question is that this term, this particular term here, is very protected. And this term we can compute from supergravity, even independently of the UV completion of the supergravity.
Okay.
All right. Okay, so as I said, for this problem, one can get even a little bit more. Instead of just S2 cross S1, I can have an answer for the topologically twisted index, the contribution to the logarithmic term in an arbitrary Riemann surface of genus G. So this is essentially some properties of these formulas. And again, so more generally for the ABJM localized on a Riemann surface of genus G, topologically twisted, I can construct the topologically twisted index, and the contribution to the log n is given by this 1 or minus 1 minus G over 2. So that's a slightly more general answer, and that's the answer that I want to pursue on the gravity side. All right, so now we're done with this introduction. So let's talk about the bulk now. So holographically, ABJM describes a stack of NM2 branes. They probe the C4 ZK singularity. And then the low energy, of course, we know is 11-dimensional supergravity. We don't know the full thing, and as was already noted, but we know the low energy theory. And so the index was computed for ABJM, and that index contained the topological twist. The topological twist will map to magnetically charged asymptotically AdS4 black hole. So this is a solution in the 4-dimensional language, but this solution can be embedded in 11 dimensions according to this, well, with this prepotential, and this is well understood. But I didn't want to clutter too much the slide. So again, the part that is important for us is this 4-dimensional black hole. So you can see there's a magnetic charge. There's no electric charge. So this is the black hole that corresponds to the topologically twisted index. Now, the Bekenstein-Hawking entropy is quite non-trivial, and I wanted to write this formula here so that you see, you get some idea that this is, there's a lot more going on than just some matching of powers. All right, so this is the expression. This expression, you can see, yes?
Yeah, so do you consider a fixed k all through in your calculations, or do you consider other limits as well?
Right, no, in this calculation case, thank you very much for the question. So k is fixed, n is large. So this is the M theory limit. That's what I'm discussing the problem in M theory.
I see.
Okay, thanks. But anyway, so here's the entropy. You can see it's a very complicated combination of the magnetic charges, and this all is reproduced by extremizing the index. So again, now I restate my goal is to compute these one-loop corrections around this supergravity background in 11-dimensional supergravity. All right, so so this is a phrase that I really like, and this phrase was introduced by Ashok Sen, an IR window into UV physics. So Ashok Sen, as I said, has pioneered the study of this logarithmic correction to the entropy of asymptotically flat black holes. So logarithmic corrections are determined macroscopically from the gravity side from the massless particle spectrum. So they are completely insensitive to the UV completion of the theory. That's why they are robust. I would try to show you, try to convince you a little bit more of that point. All right, so a consistency check, therefore they provide a consistency check for any enumeration of quantum black hole microstates. So if the topologically twisted index in the field theory side is the UV complete theory and gives me this answer, that answer must be able to be reproduced from this low energy massless particle spectrum of supergravity, which we know, right? So as I said again, Sen and collaborators have checked many black holes in string theory and challenged loop quantum gravity using this kind of analysis. And again, this provides a deep insight into the Strominger-Buff accounting. The microscopic realization of also Strominger has shown that these logarithmic corrections are another or pass test in the context of curve CFT. Now, a very similar computation to what I'm going to present was performed a while ago by Bachadaria, Grassi, Marino, and Sen, and this is for the free energy of ABJM, and there you can compute that the logarithmic term that comes from the exact field theory answer is -1/4. So we will see that for the black holes is slightly different, and we expect to get this -1/2 on the field theory that I show you numerically. Oops. All right, so let's talk about logarithmic terms in one loop effective function. So one loop effective function is equivalent to computing basically determinants, all right? And for a given kinetic operator A, one naturally defines the logarithmic of its determinant according to this form. These are the eigenvalues. But I use prime here to denote that I sum over non-vanishing eigenvalues. So a clean way clean and convenient way to define the determinant of an operator is to use the Higgs kernel, which I define formally like this here. So this is the operator, and this is some basis eigenbasis. Now the Higgs kernel contains information, and this is a subtlety, but it contains information about both the zero and non-zero modes. So what we need to do to compute the determinant that I'm after is to use the Higgs kernel, but subtract the number of zero modes. All right. And then another important fact is that the Higgs kernel admits a Seeley DeWitt expansion for a small tau. This is essentially the physics of this expansion is an expansion around flat space. So you can see that the first term in this expansion, n equals 0, corresponds from integrating this eigenvalue, which essentially is like a bunch of Gaussian integral, and gives you this tau to the -d/2. And then I have to compensate by the fact that I'm really not in flat space. But that's essentially the physics of this Higgs kernel expansion. So now these coefficients are not necessarily combinations of Riemann tensors and other diff invariant combinations, right? So I know that this is a small print because I just want to give you a flavor of the comment I made at the beginning. So if I want to now compute the determinant, I use the Seeley DeWitt expansion. I'm subtracting the zero mode here. The Seeley DeWitt expansion has basically this infinite sum, but if I'm interested in the logarithmic term, then I need this n to be d/2. You can see here, right? So this is the only term that would give me, when I integrate the tau/tau, that's the only term that can give me a logarithmic correction that would enter through this cutoff, all right? So basically, the logarithmic contribution will come only from this coefficient, d/2. And of course, I need to know some information about the zero mode. And now, on very general grounds, diffeomorphic invariance, there's no coefficient that you can write, this coefficient is 0 in odd dimensional spaces. This statement, you know, in a different guise. You know that there are no anomalies in odd dimensional spaces. And this is essentially what this statement means in this language. The anomaly is given essentially by this coefficient. It's non-zero in 2, 4, 6, etc. But in 11 dimensions in particular is 0. So now let's summarize what has happened. So first of all, I show you that this computation is very robust. The coefficient of the log is independent of the cutoff because the cutoff enters in the log. So I shift the cutoff and the coefficient doesn't change. In odd dimensional spaces, which is our case, 11 dimensional supergravity, the coefficient of the log can only come from zero modes or boundary modes. So it doesn't come from this AN over 2 because that is 0. All right, so essentially the corrections to the entropy that I want to compute are going to be the standard thermodynamics, and then this is my one loop effective action. And then of course there's some ghosts that I have to treat separately. This -1 to the D is essentially to account for bosons and fermions, and the 0 modes, I have to take them into consideration separately. But that's essentially what I need to do. Again, the key point is that the coefficient of the log is robust. It doesn't depend on the UV cutoff. And the main contribution that I would have gotten is 0. So I only have to worry about 0 modes to do this computation. So the structure, this is the structure of logarithmic corrections in 11-dimensional supergravity. So again, this -1 is because I subtract first the 0 modes that were already in the heat kernel, and then I have to add them with the appropriate measure, and then I compute the dose contribution. All right, so for 0 modes, here I'm going to maybe move a little bit faster, but essentially the 0 modes that we are interested will come from, if I look at the non-extremal black hole, this is a little bit of a departure from the black hole that I presented to you, but again, this is a subtlety that was also understood previously for asymptotically flat black holes. To do this computation, you have to arrive through the non-extremal branch. So the Euler characteristic for this non-extremal black hole is given this 2, 1 minus G, and I can relate that to basically the number of 0 modes from 2 forms using essentially essentially I can relate that number, the Euler characteristic, to the number of 0 modes of 2 form 0 modes. And essentially the answer is that in the non-extremal black hole, this is the number of 0 modes that I need to, the number of 0 modes that come from 2 forms in 11-dimensional supergravity. Let me try to now put this in context. Why am I talking about this 2 form 0 modes? So in 11-dimensional supergravity, I have the graviton, gravitino, but I have a 3 form. Now to quantize a P form, I require P minus J plus 1 form ghost fields. So essentially, this is something very nicely explained by Siegel in the 80s. Essentially, ghosts need ghosts. So if you have, so why do you need a ghost? Because the P form has a gauge invariance, which is a P minus 1 form. But you can see that that P minus 1 form, when you try to quantize that or to put that into your computation, also might have a P minus 1 gauge transformation. So you have to keep going and changing the nature of Grassmann odd or Grassmann even, but essentially this is the answer to your problem of quantizing a P form. You need to keep going with ghosts of ghost. Right? So again, summarizing this, to quantize the 3 form in 11-dimensional supergravity, I need 2 form ghosts that are Grassmann odd, and 3 1-form ghosts that are Grassmann even, and 4 scalar ghosts that are Grassmann odd. That's essentially the answer to this question. Now, not that this 3 form itself can be decomposed, cannot be decomposed as a massless 2 form in the black hole and a massless 1 form in the compact dimension, since S7 does not admit a non-trivial 1 cycle. So all I have to worry about are 2 form that come from the 2 form ghosts, and they have 0 modes that I just counted. So I put together, okay, so this is the contribution of the ghost to the path integral. I wrote here the action, but that's not important. So the logarithmic coefficient again will come with this term. I already computed this for you. So what I need to do is to put it together. I still have to compute the measure, the appropriate measure for this field, which is this beta 2. This is a standard computation. You just have to look at the measure, make sure that it's properly normalized, and you know how the metric scales. So from there, you see how a 2 form will scale in your path integral. So when you put all that together, you get that the 1 loop contribution to the effective action is given by this formula here. And that precisely leads to a perfect agreement with the microscopic result.
Yeah, sorry,
yes.
Can you just go back there where you had this, the 2 form action, please?
Yes.
The slide before that.
Yes.
Yes. So here, delta D plus D delta is the Laplacian on the two forms.
Yes, it's the standard Laplacian acting on a P form. In this case, a two form.
So
Yes.
why should it be squared? Is that easy to explain, or?
I don't have a easy explanation, but it's actually, in this case, it's 2 because of the form, but it's actually P minus J. So I have the effective action written before. Maybe, okay, I have it written, maybe this minus J minus 1. But okay, yeah. I don't have a clean, easy explanation, yes.
So the power is determined by, like how many levels you have gone in the ghost number or something like that? Or?
Right.
Okay.
All right, so at this point, this is, I think we now have that supergravity gave me precisely the same number as the field theory. And that I think is a good, as Ashok-san would say, it's a good check that the UV complete answer passes this test, that I can compute that coefficient from low energy data, which I have done here, and it matches what the UV complete field theory description gave me. So now that of course involves some numerics. Yes.
So you are reproducing the log term, but I remember you also have a subleading order to be square root of n. What's the gravity interpretation?
Yes. Those do admit a gravity interpretation, but it's a little harder because it comes from higher curvature corrections. That can be done, I'm pretty sure, but it's a little more technical, and yeah, that can be done, but it's not what I'm doing. I don't have anything to say in this talk about these coefficients. They come again. They do not come from one loop supergravity effects. They come from higher curvature corrections in the string theory side. Yes.
Okay.
All right. So this computation in the field theory was a little bit. So there was some numerical aspects. Some people might be uncomfortable, etc. So let me explain a setup where these questions can be answered all analytically. And again, everything works very similarly. So there's another situation where you get AdS4 CFT3. The one that I described, ABJM, is from M2 brains, but there's another description that uses M5 brain. And in this table, I sort of summarize the key things. So now I'm considering some NM5 brain that wrap some hyperbolic 3-manifold M3. And there's a systematic algorithm applicable to this hyperbolic 3-manifold that gives you the field theory dual. Now, the gravity dual of this, in this case, instead of being some 7-dimensional Sasaki-Einstein like S7, is going to be this product of the hyperbolic space and some squash S4. And then you can compute everything. But for me, the most important thing is that the length of the space scales different with the rank of the gauge group. That's essentially what I want to take from this table. This again is a generalization of AdS CFT, but instead of starting with M2 brains, you start with M5 brain wrapping some manifold. All right. I guess all these dots are bothering me a little bit, but anyway, so one important property is that these partition functions can be written, the partition function for these theories can be written as an expansion, kind of like the Bethe-Ansatz expansion, but you have this operator. So one is called handle gluing and the other one is called fibering. You can see fiber P and handle gluing sort of G because it's the genus that you can think of. This is, again, very well understood. Cyril Closet and collaborators have worked on this extensively and have a lot of results. But again, this is for people who have followed this is more in the 3D correspondence. All right, so what I take from the 3D correspondence that is important for us is that the building blocks, these fibering and handle gluing operators, the building block of the partition function can be read directly from Chern-Simon theory on PSL NC. All right, so the fibering operator is proportional to the classical action. This is this formula here. And the handle gluing operator is proportional to the, okay, this is sometimes called Raysinger torsion, but it's essentially like the quantum one loop part of the Chern-Simon theory. So I have gone to a setup where I can read the partition function from ingredients that come to me from Chern-Simon theory. That's essentially the key thing. So this computation, as I said, I just have to borrow results from the math literature about Chern-Simon theory, and I evaluate the partition function that I'm interested. So you can see this is the leading piece here, n cubed, and the logarithmic term will be g minus 1 log n. So this is, field theory give me the logarithmic part and the leading piece. And of course, this is a completely analytic result that uses some as expansion of mathematical results in the literature. I don't know why my screen keeps getting all these points. All right, so here's the gravity solution. Again, the point in this talk is not that I will convince you of every detail in this slide, but the main idea here is that these gravity solutions are well known. You can see that there's a hyperbolic three-manifold here, locally written. Of course, I have to quotient it. Okay, sorry, I getting all this dot. I'm something with my stylus is not nice. Maybe I shouldn't use it very much. Anyway, the supergravity embedding is known in 11 dimensions. Do you see my pointer here?
Yes, yes, we can see it. Okay,
maybe I just follow with the point. So the black hole will be here. This is the AdS4 solution. There's the hyperbolic three-manifold, and then there's these two parts will become Son squashes 4. This is again, there's some detail here, but the important thing is that this I can write. It's a well-understood solution of 11-dimensional supergravity. Just to be a little bit more accurate, so Pernici-Seskin found this solution in 7 dimensions first, then Acharya, Gauntlet, Kim, Waldron. So all these characters, they found a better description, which is the one that I presented. Okay, but the idea is that I can even compactify on the hyperbolic three-manifold part and obtain a regular, very universal sector of gauge supergravity. And this admits a solution, which is this black hole with magnetic charge. And the area, of course, the entropy of this black hole coincides precisely with what the answer from field theory is. But moreover, I can do I can do the one-loop computation very similar to what I sketched for you, but I now know, again, there's a two-forming AdS4 that is contributing. I compute it. The only difference here is that the L scales different with N, which when I plug, I get precisely the answer from field theory. So this is another instance where I can do my microscopic computation. That's the field theory part. And I do my macroscopic computation and I get precise agreement. Moreover, at that time, I issue a challenge to the field theory community because the computations require that the first Betti number of this hyperbolic three-manifold would be vanishing. So, but if it is non-vanishing, what I need to do, I know. I have also a three-forming in supergravity, and now I can form a three-forms zero mode by computing, by using a one form from the hyperbolic three-manifold and the two forms that I already had. And that would also contribute to the one-loop effective action. And it contributes precisely this term. So this was the full answer for arbitrary manifolds. And now, that was at the time a challenge, but now people have done the computation more generally on the field theory side, and now they obtain precisely this expression. Okay, so let me, this discussion has been all about magnetically charged black hole. Now let's discuss one rotating black hole. This is again a rotating black hole that I can obtain in the same sector of the 4D supergravity that I wrote here. Okay, so same theory, but now instead of this solution, I can consider this solution, a rotating black hole, again, supersymmetric. Of course, it's a lot more complicated. If you are not familiar with rotating black holes, you will not become familiar now, but this is just to give you an idea of how flexible this scheme is. So the entropy of this black hole can be computed directly from the area. These are supersymmetric black holes, so there's some constraint that allow me to write the entropy using different quantities, either angular momentum and charge, or just charge. I can compute the entropy function by evaluating the on-shell action on the gravity side, and of course the entropy comes from extremizing or Legendre transform of this quantity. So this is just to try to make the connection easier. On the gravity side, I provide this entropy function. And when I extremize it and everything, I will get the entropy of the black hole. So that's precisely the entropy function that I computed from the field theory side with Benini and Dongmin Gang. So it's precisely the same. So that, again, provides a clear description of the leading piece. But for the subleading piece, we can also, again, the computation I had already done very generally. So you can see that this matches precisely the field theory answer. Sorry, this is the field theory answer that matches what I have computing in supergravity. So again, there's agreement, and now this is even for rotating black holes, slightly more general. So, all right, so that is the part of the talk that was focusing on AdS4 black hole. So I described how I can do an 11-dimensional supergravity computation that give me access to the logarithmic corrections, and that matches precisely with the field theory whenever the field theory is available, be it numerically for M2 theories on M2, or analytically for these theories on hyperbolic three-manifold from M5. All right. So now, any questions about this? Because now I'm going to talk about something slightly different.
Sorry, can you say a bit more about how did you get this this login from the field theory side on this? Like, how did you compute in these TN theories? This is localization, or what is the?
Right. So good. Okay, I don't have. Okay, I guess my slides are not very nicely prepared here, but so essentially, from the field theory side, you can look at this. Well, you have these two Chern-Simons and different. So you can construct you can construct different observables in TN theories by just looking at properties or relationship between these two coefficients. And that's all that you need to do, because of course the action comes, okay, in localization you see that the Chern-Simon very nicely gives you the idea of these holomorphic blocks. So it becomes constructing the partition function becomes a problem on how you're gluing these holomorphic blocks. So for the superconformal index, you have to glue it in a certain way and then take the limit. And that's what we have done.
Sorry, so maybe I just, so your statement is that there is some basic blocks, you know what the contribution to the index from them are, and then you can put them together using the standard.
Exactly. So these are not the holomorphic blocks. These are different building blocks. But of course, in terms of the holomorphic blocks, it's easier because knowing the holomorphic blocks, then I have let's say the holomorphic blocks are beta alpha. So then my partition function will be G alpha beta, beta alpha, beta beta. And then I just choosing G tells you what partition function you're computing. These are not these particular blocks, but they are related. Okay. I guess I might have been a bit confused.
So you can prove in general, did I understand that right, that you can prove in general that the B1 dependence is like what is shown in this slide for any M3, for any hyperbolic manifold M3?
Yes.
Because for some general property of the Chern-Simons theory on that, this PSM.
Exactly. Yeah.
Chern-Simons theory on that. Okay, thank you.
My pleasure. All right, so now I want to talk about some new recent developments about microscopic counting of AdS5 black hole entropy. So, okay, electrically charged rotating and asymptotically AdS5 black holes in type 2b were discovered or written down by Gutowski-Real, 2004. Chon, Swedish, Lu, and Pop did a more general, presented the more general situation with including a non-extremal black holes, etc. And then, of course, this is the paradigmatic example of AdS-CFT. So naturally, of course, you would like to understand it microscopically, and that was a very nice work. The first attempt by Kini, Maldacena, Mingwal, and Raju in 2005, exploring whether the superconformal index can capture the black hole entropy. But now, more recently, at the end of 2018, three seemingly different resolutions to the microscopic entropy of AdS5 black holes have been proposed, one by Cao-Bisset, Casani, Martelli, and Murthy, using localization, some ideas of localization. Choi, Kim, and Nangun, they use the partition function of n equal 4 plus a constraint, and they, again, provided the leading order was the same. And Benini and Milan used the superconformal index, but in some Bethe-Ansatz formulation, and also computed this index. So one of my old mentors, Michael Duff, used to like this phrase, an embarrassment of richness. So when you have, life is too good to be true, right? So you have now 3 completely a priori separate explanations from the same thing. And this is, as you see, this is the perfect scenario to send in the logarithmic police, because, okay, just like with the Born energies, right? So many ideas, many observables may be look the same at the leading piece, but the sub-leading piece might be different, and that's where the logarithmic police can really determine who is the culprit, who is actually the dual of the entropy. And this is essentially some of the work that I'm trying to do now with my colleague Jim Liu and my graduate student Alfredo Gonzalez Lescano from CISA, and a graduate student here in Michigan, Jung Ho. So I want to tell you a little bit about this. I think it's very exciting. And this week there were already like 4 or 5 papers about this topic. So it's a burgeoning area, but it's quite interesting. So let me tell you what very preliminarily I have to say about this. So one can treat these problems a little bit more broadly by considering toric quiver gauge theory. So some class of theories that contain many gauge groups. So NV gauge group, they contain chiral fields that transforming by fundamental representation with respect to these gauge groups. So these theories can be represented with toric diagrams, and they have D vertices, each of which can be associated with a U1 flavor symmetry. Again, there's a lot of studies about these theories, and for these theories, with Alfredo, we computed the superconformal index using the Bethe-Ansatz. So that I can talk about that class more generally, but roughly there are 2 approaches. So one approach to the superconformal index uses this elliptic gamma function presentation. So again, it's a matrix model. So here are the holonomies, and again, C and U are related usually as this exponentiation. These are elliptic gamma functions. And then there's the representation of Benini, which is more along the Bethe-Ansatz representation that I discussed for the topologically twisted index. And this H is essentially the Jacobian of going from one kind of variables to another, right? So, but then there's a solution. This solution was understood by various people, including my colleagues here in Michigan. There's a general solution that we can show is a solution in this more general context of quiver gauge theories, toric quiver gauge theories. The important thing is that you can compute now the superconformal index for all this class quiver gauge theories, and of course, the leading term gives you what you expect. So this is the entropy function that leads to the entropy of the corresponding black hole. But now this is a slightly more general. But of course, my talk is about precision holography or precision computation. So I want to go beyond that. And to do that, I just, again, this is not even very complicated. I just need to systematically expand in large N all the terms in this expression, which I do. So there's some contribution that come from, so I'm assuming that I'm writing the partition function using this language, okay? Z and H are just components of the partition function so that you can track. So Z will give me the part that is the leading piece for the entropy, and it gives me this n log n, but it has NV number of vector multiplets, and then some constant, etc. So this is like a normalization factor, and that gives me a log n and nothing else. So this H, which was in the partition function, precisely give me negative NV n log n. So you can see that when I put everything together, I get a very nice answer for the log of n, which coefficient 1. So this is a very beautiful result. So this is for n equal 4, which is of course one of our main interests. So now we know very robustly using the Bethe-Ansatz approach that the coefficient is log n with coefficient 1. So this is now a microscopic logarithmic correction to the entropy. It would be nice now to do the computation in gravity. I will argue, it's a very complicated computation, but now it is, field theory has a prediction for that answer, 1, okay? Now, as we were sure that, okay, we did this computation for the index in the BT-ANSAC presentation, so now we are going to do it for the, using the elliptic gamma function presentation. And there,
hello? Sorry.
Yes.
I just wanted to interrupt. So you had, you know, like you didn't mention it, but you had it in your slide. For this, of course, to get this n square term, you need to like, you know, deform the index in a certain way to avoid these cancellations and so on.
Absolutely, yes, absolutely, yes.
So,
yes.
so you know, like, do we understand this procedure enough? This is the question, to kind of control these subleading corrections. So you seem to be able to do that. Do we understand them sufficiently, that what one should do and how the subleading corrections all work in a very good way now? You know,
okay, so I am assuming that I'm using complex chemical potentials, and then I have to be very careful about the range where they are defined. But there are some issues. I agree with you. There's a deformation that one has to be very careful. But for computing, okay, in this context, for computing this coefficient, I don't have to. Again, this is something that I can compute using just. There are some subtleties, but I am assuming here that the main contribution from the BT-ANSACs are specific kind of solutions. This one that I wrote here.
mm-hmm.
And that I can more or less argue it makes sense. But again, I don't have a proof if that's what you're hinting at.
Mm-hmm. Okay, but for example, if you wanted to compute subleading corrections, you know, like, is there some controllable way of doing it, or is it something specific?
Yeah, this is where, okay, for the BT-ANSAC presentation, I show you that there, well, okay, my understanding, again, everything is very preliminary. There's no paper out yet. But what I want to say is that for the BT-ANSAC approach, in which I assume, my only assumption is that this is the solution that contributes the most. And with that, I can get very cleanly this coefficient. Now I want to explore it in the other presentation. And I will show you that not all is well in the kingdom of Denmark. So I will show you some problems.
Okay, thanks.
Okay, so one important thing that was the same for all these models is that oftentimes people needed to take something called the Cardy limit, which is essentially sending one scale to be a lot smaller than the rest. In this case, is this tau. So when tau goes to 0, all the holonomies collapse to 0. Okay, and this is where, especially this approach using the elliptic gamma function was rooted on that fact. But now, and this, I guess now I understand better the question. So now I cannot just sit on this point, because that might kill some of the logarithmic correction that I'm after. So I have to first be away from this tau equals 0 point, and then analyze my logarithmic term there, and then take the tau go to 0 limit. These two things might not commute, and I have to be very careful. I did not have to be careful with the BT-ANSACs, because the BT-ANSACs is written nicely for an arbitrary tau. I don't have to sit at this Cardy limit. But in this approach, if I need to sit at the Cardy limit, I need to understand if I'm losing something when I get there. I hope that this maybe is the question that I did not clarify before. All right, so this plot here is shown again. This is all preliminary. This again work with my student Alfredo Gonzalez from CISA, Jung Ho Hong, who's a PhD student in Michigan, and my colleague Jim Liu. So one thing that we are doing is essentially, let's take a saddle point equation for this presentation of the superconformal index and solve them. Okay, when you solve the holonomies, what you get is these blue dots, right? That you can approximate with this line. Now, this solution, the basic solution, as you can see, is a solution that is essentially distributed along this line. So it should go from this red line, this red dot, to this red dot. And this is not what we're getting numerically. So numerically, we're seeing that there's a difference in the solutions as soon as you move from tau different from 0. And this we first noted numerically, but now we have even an understanding analytically of what this difference is. So to summarize right now, things might change, but right now, the presentation of the index that uses this gamma expression has corrections at the Cardy limit, but these corrections are n-squared correction. These are not subleading corrections. So now even the n-squared term is different when you start moving away from the Cardy limit. All right, and of course we want to clarify this part and then move on to the logarithmic term and see if it even coincides with what we expect is the logarithmic correction from the other approach. All right. So with that, I want to conclude. Again, as I said here, stay tuned because we are exploring this. We have some results, and we hope to have some paper coming out soon. But the situation is really subtle, and the main claim at this point is that even the leading point, the leading order n-squared term gets a slight contribution when you move away from tau, which is not the case for the Bethe-Ansatz approach. All right, so I want to conclude now just saying that, so this is something I did not have time to talk. It's a little technical, but it would have been great. I just had to choose. But so in all these computations that I did about this logarithmic term, I did not emphasize it, but it was important that I did not go near the horizon. So typically, all the quantum entropy formula that Sen used for asymptotically flat black holes, you will go near the horizon where you had an AdS2 geometry and do your computation there. My computation really was in the asymptotic boundary near AdS4. So that means that there's still some work to reconcile the near horizon asymptotic region and the AdS at the quantum level. So this is a very interesting problem. It's a technical problem about computing quantum correction, but of course what we know is that AdS is of course different from flat space. AdS is a box, and it allows some hairy degrees of freedom that maybe the near horizon approach cannot count, and that's why we necessarily need to go to the UV region. On the other hand, AdS CFT is correct, so all the information in the boundary has to be reflected in the horizon. So there are some conceptual issues that I would like to discuss some more. So for me, this is one of interesting open problem. There's a problem that, in fact, there was a question about other terms, the higher curvature term. This is a little bit like Maldacena-Strominger-Witten. This is a good precedent for M5 brane computation. They managed to show exactly this higher curvature correction. And then there's some machinery. There's Wolf entropy formula that can help you. But I think this is another interesting problem that can be tackled in this context. And so more interestingly, which is what I'm working on right now, so this electrically charged rotating AdS5 black hole entropy explain, people have checked, okay, yes, this explains the entropy, but I don't think has been explored deeper. So again, there were a number of papers this week describing that, and I think that's the spirit. So we have this litmus test, so this very important test. We have an answer, and we want to make sure that all the answers agree, or if they don't agree, why. But we will understand what is the right observable for the dual black hole entropy. So the gravity computation on type 2b for this logarithmic term is very challenging. I have tried that computation on and off. And again, one of the main difficulties is, of course, that now you are in even dimensions. So even the silly DeWitt coefficient term that you have to compute, the one that was 0 for 11 dimension, is now non-zero and highly non-trivial. It's a very technically challenging question. But more generally, I want to convey the excitement that now there's a precise setup to attack important problems in black hole physics, which I think that the deep brain technology, the deep brain developments on the 90s did not provide for that. They explained the entropy, but it was hard to go beyond. Now we have field theoretic degrees of freedom, we have localization. There are many techniques and the degrees of freedom are more familiar to us. And I think that would allow us to understand a lot more about black hole physics in general. So with that, I finished. Thank you very much.
Oh, thank you very much, Leo. It was a very nice talk. So if you have any question, please ask. I don't think that people have any question.
Can I ask a question? So have you think about hi professor? Have you think about your calculation to other aspects of like hot new topics nowadays? For example, in quantity or something, have you seen any connect project? I mean, your calculations and
well, we are sorry, your voice was broken. So could you please ask the question again?
can you hear me now?
Yes, it's better now. You can ask.
So I was wondering if you can say something about the connection between your work and some new, other development in black hole physics, like complexity or some quantum information topics. Have you seen any connection between these calculations and those improvements?
Yeah, that's a very good question. I have not delved into directly trying to tackle those questions. So my main motivation is really understanding. Well, first we have understood, I think, as a community, the entropy counting. I think the entropy counting, there are some refinements to do. Things are not as they have been claimed, but for the most part, I think there's an understanding there. The next part, I think, for me is what is it that one can do dynamically? Can you actually start talking about Hawking radiation? That's what I was saying towards the end of my talk, that I think it's great to have this setup where we, on one side, we have just, vanilla flavor quantum field theory, and we can try to compute correlators and see if we see any behavior. But for me, this is in the future. Right now, all this work is about just the kinematic part, just counting, making sure that that your bookkeeping is correct. Again, it's not perfect, but I think it's coalescence to something that is ultimately correct. And the next step is to move to dynamical question. For me, the natural thing is black hole entropy. Hawking radiation, but I'm sure that complexity and all these other aspects will probably also be addressed.
Okay, so your first step is like developing this calculation for the dynamical setups.
That's in the future, yes. That I think is the next most important thing to do.
Okay, thank you.
Sure.
Thank you.
Any more questions?
Sorry. So Leo, can I ask one question about this? So in the last part of your talk, you're talking about some deviation of the saddle points.
Yes.
I did not quite completely get what is the computation that you're doing and what is the deviation and so on. Maybe you can explain it.
Okay. Yes. So let me try. Let's see. So you can see my screen, right?
Yes.
So actually, I go a little bit back here. Okay. So here's the superconformal index written the standard way in terms of hyperelliptic, elliptic gamma functions, right? So this is a problem that I can tackle as a matrix model problem. So some integral, and I can try to do this integral using saddle point. And this is what some of these groups did. They said, okay, I will do the saddle point for this, but I have to do it in some specific limit, tau equals 0. That's the Cardi limit. In tau equals 0, these elliptic gamma functions become some polynomial, so life is good. So you do it in that limit, you reproduce the entropy formula. All right. So in this approach that Benini and Milan took, essentially I have to solve some other equation whose solutions I know already, and I just plug in here. Tau can be anything. I don't need to take Cardi limits. Now, both of them, of course, give you the same leading piece. In the beta answers, because there was no Cardi limit, I don't have any worries, so I just go and look for the log n coefficient, and I find it very easily. It's this one. When I want to do that for the elliptic gamma function approach, I first have to relax the fact that they work in the Cardi limit. When the saddle point was all ui equals 0. And that might kill, being in that saddle point might kill potential log n corrections. So I have to go beyond that, all right? Now, normally one would say, probably the same solutions for the beta ansatz were solution for the Cardi, for this elliptic gamma. But I can see numerically that they are not. So the solution for the beta ansatz were a line between these two red dots. I didn't draw it because I didn't want to overcharge this. But this is certainly not the green line, which is the best approximation to the actual numerical solution of the elliptic gamma approach. All right. So, and that leads to a disagreement at the n squared level. This is a leading order disagreement between the beta ansatz approach and the elliptic gamma function approach. Just as soon as you move away from the Cardi limit, you get an n squared correction from that approach. And this is sort of a step 0. Step 1 for me is what I wanted to do is just to compute the log n there, which I will do. I still don't have the number, but that's what I meant.
Sorry, there's something particular I'm going to understand. So you have the same matrix model integral, and you're calculating its saddle point in 2 different ways, and they disagree. I'm not quite getting it. So
yes, so good. Very, very nice question. So in fact, in principle, you can say, yes, these two are representing essentially the same object, right? But it could be, again, the saddle point here is more approximate than, let's say, I assume, well, I assume no, I told you that this is exactly n. Here I'm just taking a large n approach. So there could be some subtleties that made these two things different. But my answer is, I mean, when I see this kind of, this is very numerical. So for me, this is not the truth, but very strong hint. And then, as I said, then I went now analytically and tried to look at the, expanding the elliptic gamma functions more carefully and look at subleading corrections. And I can reproduce this now analytically using some matrix model technology. So this is still work in progress, but I think the story will be that roughly a leading order, these two objects will not be the same.
Okay, a completely unrelated question.
Yes, please.
So you're talking about this M2 branes and an M5 branes on this hyperbolic manifolds and so on. But
yes,
is there something that can be done about the full non-compact M5 brane, the 60 theory and the AdS7, and black holes there?
There are actually some work. I think Marcos Cristiño had a paper recently with Jane. I don't remember the first name, but last name is Jane. So there's some work. I'm not super familiar with the work, but there is, of course, some. So I didn't mention it correctly, but anyway, these computations that I was discussing in the context of AdS5, they have been extended to AdS4, AdS6, AdS7, and of course their corresponding dual field theories. Yes.
Okay.
Now, at the leading order, right? So the sub-leading corrections, I don't think have been studied in those contexts.
Thank you.
My pleasure.
Hi, Leo. This is Gautam here. Gautam Mandal.
Hi, Gautam. How are you? Good to see you.
Hi, you too. I had perhaps a very naive question. So you discussed computation of indices, and
Yes.
so that's not exactly the same as counting, black hole states, as we know. I mean, so there are the signs and
Yes.
phases and so on. So in order to, so for example, in some of Ashok's calculations, it turns out that in some examples that the signs are all the same for the index calculation. So it becomes the same as the, so something, the equivalent of, -1 to the power f is just 1 for all of them because of the S-wave, SU2 singlet condition and some fortunate circumstances. But how does an index calculation tell us anything about counting black holes?
Good. So that's, I completely agree with you. That is a very valid criticism. I think there's not a very robust, rigorous understanding of what is going on in this case. The hope and the indications is that by choosing these chemical potentials very wisely and allowing them to be complex, you are effectively altering what would be the index and therefore getting a hold or the counting more accurately. That's something along the lines of what Ashok and collaborators showed is true also here, but that has not been discussed rigorously. So a lot of effort has been put into trying to understand how this is happening, but as far as I understand, there's no clean paper that says this is how it's happening. But an understanding is that something is in fact, the original computation that along this line for the superconformal index, I mentioned at the beginning, Raju was involved and Shiraz. So this computation even didn't even get the n squared part. And okay, now it's understood or at least accepted that is because they were restricted to real fugacities. And in that case, this is what you get. So I think the answer is lurking in properties of these fugacities, chemical potentials, but it's not have been pinned down cleanly, as in the case of Ashok, where you can relate it to a group theoretic property, and then that has not been done yet. But I think ultimately this will be done.
I see. Okay, thank you.
You're welcome.
Any more questions? Yeah, I don't think there is any more question. So in the next week, we have a talk by Park Krause from UCLA, and it is on 8th June at 9:30 Indian time. So, all right. So thank you very much. Thank you, Leo. Have a nice day. And
thank you. It's a pleasure. Thank you.
So have a nice time.
Thanks.
Bye.